Hello everyone. A very good evening to all of you. I hope I'm audible and visible. Okay, so let's wait for 5 to 10 minutes so that everyone can able to join this session. Okay, let's start the session. Hello everyone, my name is Pooja Verma. I am PMRF Research Scholar from IIT Kharagpur, and instructor for this course is Professor Santanu Chattopadhyay, Electrical and Electronics Engineering Department, IIT Kharagpur. This is a week 7 live and interactive session on digital circuits. Okay, so you can use the chat box for asking and interacting for this session. Okay, I hope I'm audible and visible. Can anyone confirm it? Yeah, okay. Thank you. Okay. Good evening. Good evening. Okay. So these are the some topics which have been covered for this week video lectures. So I hope all of you have gone through this week video lectures. Okay. So we will start the problem solving session right now. The topics which have been covered for this week is the conversion between the flip flops, which have been already done in week 6, as well as that is done. Some of the topics are left which have been covered for week 7. Then register applications, shift register applications, then counter and different types of counters and their design, synchronous counter, ring counter, Johnson counter, and then finally finite state machine has been started. That will be carried out in the next week also. Okay. Okay, so these are the truth tables, or you can say that characteristics table for the different flip flops. So we will require during solving the problem. So here I have put it. Okay, so let's start the problem solving session. Week 7. So assignment 7 questions are there. So first question is, how many flip flops will be complemented in a 10-bit binary ripple up counter to reach the next count after the count 1 0 0 1 1 1 0 0 1 1 1. Okay, assume all flip flops are positively triggered. So any guesses? Okay, so don't see the answer. How many flip flops will be complemented in a 10-bit binary ripple up counter to reach the next count? So present count is 1 0 0 1 1 0 1 1, right? So in order to reach the next count, we have to apply one clock, or you can say that we can add 1, so that will be shifted to the another one. Okay, so 0 1 1 0, and again 0 0 1 0 1 1 0 0 1. So now we have to see that how many bits are complemented, so that can be applied in the flip flop. So how many bits are changed to reach the next count? It is a next count, right? Next count, it is a present count. Present count. Okay. So how many bits have been changed from the present count? So 1 to, from till here it has changed. So number of bits have been changed is 4. So 4 flip flop will complemented or changed. Okay. So already you know that flip flop can store a 1 bit. So store these bits, so that many flip flops are required. So they are asking how many flip flops will be complemented in a 10-bit binary ripple up counter. So 4 bits are changing, so 4 flip-flops will be complemented. So that's why answer C will be the correct answer for this question. Okay. So yeah, have you understand this question? Okay, so I hope all of you have understood this question. So moving to the next question. The next question is, a binary ripple counter uses flip-flops that trigger on a positive edge of the clock. What will be the count if the normal outputs of the flip-flops are connected to the clock input of the next stage? Okay, so what will it will count? Option A is a count up counter, or option B is a count down counter, option C is a ABCD counter, option D is a gray code sequence generator. So question is given, a binary ripple counter uses flip-flops that trigger on the positive edge of the clock. What will be the count if the normal output? So already we know that the flip-flop has two outputs, right? One is normal, another one is complemented, right? This is a clock. Here the input, let's for example it is a JK flip-flop. Okay, so they are saying that what will be the count if the normal output, of the flip-flop are connected to the clock input to the next stage. So let's take two flip-flops. It is for example, they are saying that the normal output of the first flip-flop are connected to the clock input of the next stage. Okay, so it is also JK flip-flop. That, right? So for here we can this flip-flop G1, it is a flip-flop 2, J2, K2, so J1, K1. Okay, so in order to check, so let's I am giving it one both the flip-flops input J1, K1 and J2, K2. So let's see what it is it will count up or it will count to down, or it is a BCD counter or a gate code sequence. So for checking, for example, when the clock pulse will come, that is it is written on the positive edge of the clock. So that means it is when 0 to 1 will, so that will be a positive edge clock. Then what will be the we need to see the output of the what it will count. So initially all the counters in the position of 0 0, right? When clock 1 will appear on this, so already we know that G1 from the characteristics of the JK flip-flop. So for 0 0 0 1 1 0 1 1, here we are already fixed the input at 1 1. So let's see for that. It will toggle, right? Output will toggle. Here 0 1, it is I think T1. Okay, so at the first clock J1 that are J at 1, so already it is 0, so toggle means it will change 0 to 1, 1 to 0. So for example, the output of the Q1 will toggle, that is 1. So if it is 1, then clock is also triggered, right? Because the output of Q1 is 1, then it will be the next JK flip-flop will be activated, and here the inputs are also 1 1, so it will also toggle, so it will be a 1 1, right? Now let's see for the next clock. When the second clock pulse will be there, then G1 and K1 already 1, right? So for the next clock pulse, it is 1. So again the output of Q1 will toggle, it is 1, so it will go to 0, right? Now Q1 is 0, then this flip flop will be deactivated, right? It will not activate. So in that case, then output, there is an output, so it will be the 0. No, it will be the 1 in the same state, right? So this side is Q1, Q1 is 0. Just a minute. Okay, Q1 is 0, right? And Q2 will be in the same state. Okay. So now when the next clock pulse will come, for example, clock pulse 3 will come, then again J1 K1 is 1, so again it will toggle, so it again goes to 1, Q1 will be 1, and when the Q1 will be 1, then again this flip flop will be activated. Okay, so then it is already is 1, so it will toggle to 0, right? Now when the next clock pulse will come, so J1 K1 is 1, again it will toggle, that means 0, it has gone to 0, and when it is 0, Q1 will be 0, so this flip flop will not activate because the clock pulse is 0, right? So when it is 0, so it will be the in the same state, the output will be the in same state. So from here we can see that the outputs, it is initially 0, then it is in 3, it is 2, 1, 0. That means it is down counting, right? 3 to 1 0, 3 to 1 0. So the answer is B, a count down counter. So a binary ripple counter uses the flip flop that trigger on the positive edge of the clock. What will be the, so it will count down if the normal output of the flip flop are connected to the clock input to the next, then it will count the down, it will act as a down counter. Okay, so I hope you have understand this question. So moving to the next question. Okay, so next question is, the content of the 4-bit register is initially 0 1 1 0. The register is shifted 6 times to the right with the serial input. Okay, someone is asking, yeah, ma'am, can you please explain previous question? I didn't understand. Okay. Okay, I will repeat that question. Okay. So it is given in the question, a binary ripple counter uses flip-flop that trigger on the positive edge of the clock, right? What will be the count if the normal output of the flip-flop, that means this is it. Any flip-flop has a 2 outputs. One is normal output and one is a complemented output, right? So they are saying that if the normal output of the flip-flop are connected to the clock input to the next stage, so that means that normal output of the first flip-flop is connected to the next stage clock input, right? Here it is given clock input of the next stage. So I have connected this clock signal to the output of the first stage. Okay. So for example, I have taken the JK flip flop. I have put it both the inputs at 1, and the normal output of the first flip-flop have connected to the next stage clock input. Okay, so initially all the outputs are 0 0, right? Q2 and Q1 all are 0 0. Okay, so when we have applied the first clock pulse, so what happened at what will be the characteristic table for the JK flip flop? When the both inputs are 1, so that output will be toggle either 0 then 1 then 0 1, right? Toggle means 0 1 0 1. Okay, so when here we have fixed the JK to 1, both the flip flops. So when the clock pulse will applied, first clock pulse will come, JK is 1. So previous output is 0 already, so it will toggle to 1, right? When the first clock pulse output is 1, then second flip flop will be activated, right? Otherwise it will act as deactivated, because if it is a 0 means there is no clock pulse. Whenever the first flip flop output is 1, then it will be activated. So first flip flop output will be 1, right? Q1. When the first output flip flop output is 1, then the second flip flop will be activated. Then again here the input is given J2 K2 set to the 1, so it will also will toggle it already it is in 0, then it will be 1. Now when we will apply to the next clock pulse, that means second clock pulse, then what will happen? So it is already set J1 K1 to the 1, so again it is 1, so it will toggle, that means it will change to 0, right? When the output of the first flip flop will be 0, then the second flip flop will be deactivated, means that will not work because clock input is 0 here. So it will remains in the same state. The output will be the same. That means it will be the 1 only. Okay. Now when the next clock pulse will come, then again it will toggle. The Q1 will toggle. It is in 0, then it will change to 1, right? That will be the 1 Q1. When the Q1 will be 1, then second flip flop again it will be activated because the clock input is connected to the output of the first flip flop. Okay. So again when it will be 1, then again in that case that second flip flop will also toggle, change that state 1 to 0. Okay. Now when the next clock pulse, fourth clock pulse will become, then again the Q1 will be toggle, it will 1 to 0, right? When it is 0, then output will be 0, then next flip flop will not activated because the clock input is 0, so it will remain in the same state, that means 0 0. Okay, so if you continue to do that, it will repeat the same, that means 3 to 1 0, because we have taken here the two flip flops, so only 4 cases are there. You can check it on the 3 or 4 by taking the 3 or 4 flip flop also. Okay, for example I have taken only the 2-bit flip flop. Okay, so from the here we can see that 1 1 it the output of the Q2 Q 1 1 1 0 0 1, that means 3 2 1 0, that is counting downwards. 3 2 1 0, that is called down counter. Okay, so I hope now you have get this question. Okay, okay, thank you. Okay, so moving to the next question now. So next question is the content of the 4-bit register. Okay, thank you. Yeah. The content of a 4-bit register is initially 0 1 1 0. The register is shifted 6 times to the right with the serial input being 1 0 1 1 1 0 0. Inputs are applied from the right to left. What is the content of the register after each shift? So here it is given the content of a 4-bit register. is initially 0 1 1 0. So first we need to make a 4-bit register. So we are taking the 4D flip-flop. Okay, clock. Here we are applying the clock pulse to all the registers. So it is a D input. Again the input to the connected the next, because it is a shift register. So here we are taking serial in, serial out shift register. Q. We can take D1, Q1, Q1 dash, or D2, Q2, Q2 dash, D3, Q3, D4, Q4. Okay. So already here it is given the content of a 4-bit register is initially 0 1 1 0. We can say that already it is stored in the flip-flop. Okay. So the register is shifted 6 times. We have to shift it 6 times to the right. Okay. That means this side to this side, from here to here. Okay. And the serial input is given 1 0 1 1 1 0 0. Okay, inputs are applied from right to left, means this first 0 will be gone, then another 0, then 1 1 1. Okay, so what is the content of the register after each shift? Okay, each shift, what will be the content of the register? Already it is stored 0 1 1 0. Okay, so we can say that initially the content of the register is 0 1 1 0. Okay, now we will apply to a clock pulse, then it will shift to the next bit. When it will go on to 0, so what will be the content? That means that the content will come this side. So it is 0, so 0 0 1 1, right? Because it will shift to this side. So when the 1 input will come, so it will shift to this side. So here it is input is 0 first, so it will shift this side, so that 0 will be there, and the next bit shifted to the this flip flop to this flip flop to this flip flop. Okay, now again when the next clock pulse will come, then again one shift will be there. Okay, so next bit is also 0, right? So again 0 0 0 1. Okay, right? That means that will shift to the next flip flop to next flip flop to next flip flop, because clock pulse is given to the every flip flop. So it will shift to each flip flop. Okay, now again when next clock pulse will be applied, then this one will come to this flip flop and all other bits will shift to one bit. So again 1 0 0 0, right? When again we will apply to the next flip flop, then this one will come to this flip flop and all those bits shifted by 1 1 place. So 1 1 0 0. Now again apply to the next flip flop. So the content will again shift. This bit will come this flip flop and all other content will be shifted to one bit. So 1 1 1 0. Okay, okay, so now again apply to the next flip clock pulse, then again it will shift to one bit 0 1 1 1. Okay, so they have asked for the register shifted 6 times here. Sorry, it will be the overlap. So 6 times it is given. So now we need to check 1, 2, 3, 4, 5, 6. So only one bit are left. So you can check with this on also. So when then again it will come to this flip flop. So 1, 0, 1, 1. Okay, they are asking for what is the content of the register after each shift. So we can check from the options. So first one is 0011, then 0001, then 10000, then 1100, then 1110, and 011. They have asked for only 6 times. So we can take from here to here. Okay, so option C is the correct answer for this question. Okay, this is a 7th block. So that is shifted. So they have asked for only 6 times. So we need to check only 6 times. Okay, for each. Okay, so I hope you have understand this question. Okay, so let's move to the next question. Okay, so I hope all of you know that this question answer. So the characteristic equation of an SR flip-flop is, what is the characteristic equation of the SR flip-flop? Please answer in the comment box, at least try to answer this question. And then I will go through the brief description. Yeah, try to answer. Yeah, yeah, Harsa plus R dice Q. Okay, D. Okay, let's check. So already we know that characteristic equation of the SR. We need to find out the characteristic equation of the SR flip-flop. So what is the truth table for SR flip-flop? Okay, so S R to n plus 1 next stage output. This is the input. So here we are given 0 0 0 1 1 0 1 1. So it will be the same state or hold. You can say that it is a 0 1. Don't care. Already we know that because it is a invalid in case of SR flip flop. Okay. So what will be the functional table if we want to find out the characteristic equation? Then we need to find out it the functional table. So SR given, that means present state output. This is a next state output. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 0 1 1 1. Okay, so already we know that when the inputs are 0 0, then it will hold the same output, right? So here qn is 0, so it will be the 0, and for next input is again 0 0 SR, and but here the output is 1, then it will hold the same output, right? And when R is 1, that means reset, so it will be 0 0, right? And when S will be 1, input 1 0 for these two, then the output will be the next stage output will be 1 1. And when the both the inputs of SR flip flop is 1, then invalid, that means don't care. Okay, So from here we can find out the characteristic equation of the SR flip-flop. So SR Qn, that is 0 0 0 1 1 1 1 0 0 1, right? So where the outputs are 1, we need to check. Then we will find out the Qn plus 1. So it is 0 0, here it is 1. Then again 2 zeros are there. Now 1 1 x x. So one pair coordinate will be there and one pair. So what will be the equation? This is S plus here it is R dash Q N, right? So characteristic equation for SR flip-flop will be Qn plus 1 is equal to S plus R dash Qn, right? So let's check from the answers. So option A is Qn plus 1 is equal to Qn R dash plus S. Option B is Qn plus 1 next stage output Qn R plus S dash. So option A is the only correct answer. Already we have solved this. Okay. Okay. I hope all of you have got this. So moving to the next question. So next question is a 4-bit shift register circuit configured for right shift operation. Okay, right shift operation. Okay, that means A, then A to B, B to C, C to D. It is shown. If the present state of the shift register ABCD is present state already shows 1 1 0 1, right? The number of clock cycles required to reach the state ABCD is equal to 0 1 0 0. That means they are asking how many clock cycles are required to reach this stage. Okay, so let's see how many clock pulses will be required. So A, B, C, D. Okay, so at 0 means at this stage the 1 1 0 1, right? It is already stored in the shift registers. A, B, C, D are the register, or you can say the flip-flop. So here it is given the box form. In order to simplify, when we will apply to the clock at this input, and already in the shown in the circuit, the A and D are XORed and then given to the A, okay, as a D in to this D flip-flop. Okay, so when first clock pulse will come, then what we need to do? We need to XOR A and then the input of the output of this is connected to the this A. Okay, so A and D. Okay, so 1 1. So when we XOR the 1 1, what will be the output? Anyone of you answer this? Can answer this one? XOR operation of two inputs. Yeah, correct. 0. So already we know that XOR 1 1 0 1 1 for XOR. So when the inputs are same, it will be 0. When the inputs are different, it will be the 1. The output will be the 1. Okay. Yeah, odd ones, output 1. Yeah, correct. Okay, so here A and D are same. So there, that means the output will produce 0. Okay, so that output have been connected to the this A shift register or A flip flop. Okay, so the next one A is 0 and then shift these bits, these 3 bits to this place, right? Now when the next clock pulse will apply, then again A and D XORed and output of this to gone through the D in, that input of the A flip flop, that A, D flip flop, that D in. So again what will be the A and D XOR it 0 and 0, again it will be 0, right? 0, 0, 1, 1, right? Now again XOR A and D and given to the input of D in, so 0, 1 at the third clock pulse. Okay, so 0, 1, so 1, 0, 1, odd inputs are 1, so 0, 1, 1. So now shift these bits 0, 0, 1, right? Now again shift to 1 bit, 1 and 1 will be 0 to the next clock pulse, so 0, 1, 0, 0, right? So they have asked the number of clock cycles required to reach the state ABCD 0, 1, 0, 0. So we have reached 0, 1, 0, 0. So how many clock pulses are required to reach this stage? That is 4, right? So 4 clock pulses are required, or you can say the 4 clock cycles are required to reach this stage. That is 0, 1, 0, 0. So option C is the correct answer for this question. Okay. So I hope you have understand this question. So can we move to the next question? Okay. So moving to the next question. So next question is, the race around condition occurs in a JK flip-flop when option A is both inputs are 0, option B both inputs are 1, option C both inputs are complementary, or option D G is equal to 0 and K is equal to 1. So yeah, any one of you want to answer this question? When the race around condition will occur in a JK flip-flop? So race around condition, yeah, when the both inputs are 1, then race around condition will occur in a JK flip-flop. In the JK flip-flop, if both J and K, both are the inputs are 1, for a long period of time the output will toggle as clock is high, which makes the output of the flip-flop is unstable. That in that case, that will toggle 0 to 1, 1 to 0. That is called a race around condition of the JK flip-flop. So when both the inputs are high, or you can say 1, then race around condition will occur. So option B is the correct answer for this question. Okay. Okay. So moving to the next question. The minimum number of flip-flops required to design a mod 10 ripple counter. So how many flip-flops are required to design mod 10 ripple counter? Yeah, 4. Yeah, it is 4 flip-flops are required to design a mod 10 counter. So already we know that a state must be less than equal to 2 to the power n, where n is the number of flip flop, right? So here it is n means state. So here it is given mod 10. So 10 is already given. 10 must be less than 2 to the power n. So if we take n is equal to 3, then it will be only 8. So 2 are left. So we must we take 2 to the power 4. So that is able to count every stage. Okay. So n is equal, that means n is equal to 4. So 4 flip-flops are required. Flip-flops are required to design mod 10 counter. So option C is the correct answer for this question. Okay, so moving to the next question. In general, a sequential logic circuit consists of option A, only flip-flops, option B, flip-flops and combinational logic circuits, option C, only basic gates, option D, only combinational logic circuit. Yeah, already all of you know that what is a sequential logic circuit. So sequential logic circuits are made using the flip-flops and gates also, or we can use other combinational logic circuits also. So option B is the correct answer for this question. Flip-flops and combinational logic circuit. Okay. Okay. Now moving to the next question. While converting a JK flip-flop to D flip-flop, instead of connecting an inverter between the JK inputs, a buffer has been connected, then resulting circuit will act as option A JK flip-flop only, option B D flip-flop, option C is D flip-flop, and option D is none of the above. So they are asking that while converting JK flip-flop to JK to D flip-flop, instead of connecting an inverter, already we know that when we convert JK to D, so we are giving J is equal to D and K is equal to D dash. Already you have been solved, so I am not going to solve all those things. So already the inputs, when we convert JK to D, the inputs are given to J and K, so D and D dash. That means J, K, here Q, Q dash. Here it is a clock. So here it is given D. Here we need to convert a inverter. So that J is equal to D and K is equal to D dash will come here. So they are saying that instead of connecting an inverter between the J and K inputs, a buffer has been connected. Inverter means when the input is 1, then it will produce 0. When the output will be 0, and when the input of inverter is 0, then it will invert it to 1. And what is the role of buffer? That means whatever we will give 1, it will produce output 1. If we are giving 0, then it will produce 0. That means they are saying that if here J and K, if by mistakenly we have here applied connected to a buffer, then what will happen? So we can say that in a T JK to T conversion, you have seen that J is equal to T and K is equal to T. So if we, instead of connecting the inverter, if we connect the buffer, then it will act as a T flip-flop. Okay, because in that T conversion, JK to T conversion, both inputs are same. If you have been solved this, okay, so because it will apply the both, whatever we have given to J, it will also gone to K also. So the resulting circuit will act as a T flip-flop in that case. Okay. Okay. So I hope you have understand this question. So can we move to the next? Yeah, it's the answer is the T flip-flop. Okay. So moving to the next question. So next question is between a latch and a flip-flop, which one has a higher possibility of getting input data noise propagated to the output? Option A is latch, option B is flip-flop, option C is both have equal possibility, and option D is none of them gets affected by noise. Yeah, can you answer in the chat box why? Why latch has a higher possibility of getting input data noise propagated to the output? Yeah, answer is correct. Latch has a higher possibility. Yeah, it is a level triggered, right? Because the latches are the level triggered means output can change as soon as the input is changes, right? As we applied, the output will change to the latches as whatever input will be applied, then output will change the correspond as soon as. So then, and in the flip flops are the edge triggered means it will change when it will change any state either 0 to 1 or 1 to 0. Then the output will change in the flip flop. Okay, so in that case latches has a higher possibility to getting input data noise propagated to the output because edges are level triggered and flip flops are the edge triggered. Edge triggered means the output will change at any stage either when it will change 0 to 1 or 1 to 0, but in the latches the output will change when as soon as the input will change. So that's why the latches has a higher possibility of getting input data noise propagated to the output. That's why option A is the correct answer. Okay, yeah, great. Thank you for your answer. Okay, so moving to the next question. So next question is a finite state machine with one input x. Okay, one input x and one output z. Here it is given one input only, one output. 0 dash 0 means this side is input. It will represent the input and this one will represent the output. Okay, these are the states A, B and C. Defined by a state diagram below. Assume the FSM state starts in a state A. It will start from a state A. Given is the following sequence of the input x values. X input sequence is given. What state is the FSM in at the end of the above sequence? In which state it will end when the sequence will end and what input sequence is detected by this FSM? Okay. Okay. So input sequence is given. So let's check. So I am going to from here. So it will start from A, right? So let's see when at this A state we will give to the 1, then it will change to which state? That means when we will if we will give 0, then it will remains in the same state when the input will be given to the 1, that is input. So it will change their state A to B. Okay. So first here the input is 1. So it will change the state to B, right? B. Now when it will reach to the B, then next input will be applied, that means 0. Then when the next input will be applied, so here in a B state it is given when input is 1, then it will remains in the same state, and when we will apply it to 0, it will change their state. Okay, so here the next input is 0, so that means that will change the state. That means it goes to B to C, right? Now next, it will reach to the state C. When the next input is again 0. So in the C state, we can see that in the C state also, when the input is 0, it will change the state. If the input is 1, then it will change to D. Okay, so here input is 0, so it has moved to state A, right? Now 0. Okay. Now next input is 1. So already we know that when the input at a state A is 1, then it changes the state to B. Again it will change to B. Now next one is 0, so it will again change to C, right? 1, 0, we have to done till here. Now next is 1, right? So when it is 1, so we have reached to C, then it is changing to V. When the input is 1, then it will change to B. Now again, when the input is 1, it will remains the same state, right? At B. When input is 1, it will remains the same state. Now the input, it is in state B, and now the 0 is applied, it will change to state C, right? C. Now next is 1, right? So again, if it is in state C, the input is 1, so it will move to B, right? Now again the input is C, so it will change to state C. Again input is 1, so B, then again in next input is 0, so again it will change to C, right? So what input sequence is detected by this FSM? So first one is what state is the FSM in at the end of the above sequence. So it will end at state C, right? So if state C, it will end. So now what input sequence will be detected? So in order to detect the input sequence, so in order to detect the input sequence, so we need to check in which state it is again and again moving. Okay. That means when the FSM detect a sequence, let's say BC, 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 it is constantly detect the sequence here ABC, then ABC, only two. Then it again it has changed. It must be A, then BC, then the sequence will be ABC, ABC, ABC. But here it has changed. It will remains in the same state at a two times. So we need to check here. Okay. So BC, BC and BC. From here we can detect the sequence. So when it is, we need to check from here. So it will remains in the same state at three times. BC, it only moves 1, 0, 1. That means 1, 0, 1. That is 1, 0, 1. 1, 0, 1 here, because the output will change when it will detect some sequence. So here output is changing. So only here we need to check. So that means that sequence will be 1, 0, 1. So option D is the correct answer for this question. So I hope you have understand this question. So when the FSM finite state machine detects a sequence, the output will be 1. In that case, output will be 1. Sequence is okay. So here we can see that FSM will change that their output. Yeah, FSM will change their sequence. Here the sequence will be break ABC, then ABC, then it must be gone to A, but here the sequence will be break here, but the sequence is continued to BC, BC and BC. Okay. So when the FSM detect the sequence, the output will be 1. So we can see that here only the output is 1. That means here it has detect the sequence, right? All other you can see that the output is 0, remains 0, right? Here only it detect the sequence. So here it changed their output, right? So now we need to check these three. Okay. Have you understand? The output will be 1 when the FSM in state C and input is 1. So state changes from C to B. So when the sequence will be detected. So from here we can take the input sequence 1, 0, 1. Okay, just we need to monitor. Just we need to monitor here. We will go deep down in the finite state machine in the next week. Then I will solve the more complicated problem. But just you need to, this is a simple problem of FSM. Okay, there one input sequence is given and one output is there. There is a 2-bit input output also there. So there will be more states and input output. So just it is a simple problem. So they have asked at the end which state of the and what will be the input sequence. So in order to find out the input sequence, just we need to check where it is repeating the sequence. So here it is repeating the sequence. It repeats 2 times, but here it has been broken, right? The sequence will be broken. So it will remains to be C, C to B, B to C. Okay, and the output will change here only when the state changes C to B. So the inputs we need to mark it out. So 1, 0, 1. That means here the sequence will be repeated. The sequence here detected is 1, 0, 1. Okay, input 1, 0, 1. Okay, so it will end at state C and sequence will be 1, 0, 1. That's why option D is the correct answer. Okay, so I hope you understand. So moving to the next question. Okay, so next question is if the following counter is initially at 0, 0, 0, all are in 0, 0. Then after 6 clock ABCD will be, what will be the output? That means here, what will be after the 6 clock pulse? Okay, so for simplicity, we can see that the clock pulses are given to every D flip-flop and the last D flip-flop that complemented output, right? D dash, not a normal output. That complemented output given to the first flip-flop input. Okay, so for simplicity, already we know that this is a D flip-flop. So whatever we are giving to the input, that will come to the output, right? If we are giving to the input 0, it will come, output will be 0. If we are giving 1, it will given to the output at 1, right? So I am taking for simplicity A, B, C, D. Now the complemented output, no, the output of D, here we are giving to A, right? Here it is a clock pulse, right? The initial stage is 0, 0. Initially it is 0, 0, 0. All are 0. So here we are giving clock and the after 6 clock pulse we need to check what will be the output. Okay, so I can write it as a counter. So when the first clock pulse we are giving, so what will be the initially it is 0, 0, right? So I can write here 0, 0, 0. When the clock pulse, first clock pulse we will apply it. So output of this is given to the first D flip flop. So that is, if it is 0, then initially 0, so it must be 1, right? So that means first 1, that 1 will be the 1 and all other are 0, 0, right? Now again when the second clock pulse will become, again it is 0, D is 0, so it will complement as 1 and then shift to the next one. Now next clock pulse will apply it. Yeah, now it will move like this. We need to check till 6 clock pulse. What will be the final sequence? So when the third clock pulse will, so again D is complemented. That means this one 1, 1, 1, 0. Now next clock pulse again, this 0 will be complemented. So 1, 1 are given to A. Now again next clock pulse. So it is now 1. So it will complemented to 0 and given to the A. This D flip flop. So 0, 1, 1, 1. Now the 6th clock pulse. Again it is 1. So 0, 0, 1, 1. Right? So at the end of the 6th clock pulse, the sequence is 0, 0, 1, 1. Right? So that's why option 2 is the correct answer for this question. After 6th clock pulse, the ABCD will be 0, 0, 1, 1. Okay. So I hope all of you have understand about this question. Yeah, 0, 0, 1, 1. Correct. Okay. So moving to the next question. So next question, what would be the number of flip-flops required to design mod 10 ring counter and mod 10 Johnson counter respectively? So how many ring counter and Johnson counter are, how many flip-flops are required to design ring counter, mod 10 ring counter and mod 10 Johnson counter? So already if you have gone through the ring counter, so number of states in the ring counter equal to number of flip-flops, right? For ring counter, for ring counter. So number of states is equal to number of flip flops. So here it is a mod 10, already 10. So that means 10 flip flops are required. I'm writing it as flip flop as a FF. 4 flip flops are required. And for Johnson counter, for Johnson counter and flip flops are required to count 2n states, right? So here it is given 10, that means 2n is equal to 10. So in order to find out 10 by 2, so 5 flip flops are required for Johnson counter. Okay, so for ring counter, the 10 flip flops are required, and for Johnson counter, 5 flip flops are required. So option A is the correct answer, 10 and 5. Okay, yeah, correct, n by 2. Okay, okay, so moving to the next question. The next question is, what is the modulus of the counter circuit shown below? Okay, so already it is given here. We need to find out the modulus. So it is given, this is a 5-bit ring counter, right? And the last flip flop, or you can say last counter output, is connected to the JK flip flop, where JK is connected to when both inputs are high. That means that will toggle at every clock, either 0, 1, 1, 0, right? And then the normal output is taken as a F of the JK flip flop, right? So the modulus of n bit ring counter is n, that means 5, right? For this it is a 5, only modulus of this is 5, because 5 bit ring, it is a 5-bit ring counter, and the modulus of JK flip flop, which is operating at toggle mode, that means JK is equal to 1, is 2 because it will, what is this, the two output, either 0 or 1. So overall circuit modulus will be 5 into 2, that is 10. Okay, so it will act as a mod 10 counter. Okay, already it is given 5-bit ring counter, so modulus of this one is 5, and for JK flip flop, yeah, it will act as a mod 2, so it will multiply it. In order to find out the overall circuit modulus, then 5 into 2, it will act as a mod 10 counter. Okay, so moving to the next one, what logic blocks should be placed at a place X shown if D flip flop is used, where in the previous question or this one?
In previous question, ma'am.
Okay, in previous question. Let me check. Okay, if D flip flop will be there, so most of the time when we are going to design a counter, mostly for shift registers we are using D flip flop, if you have seen, and for counter design mostly we are using JK or T flip flop. If it is a D flip flop, in that case only one state will be, then that will act as a, because it will shift only whatever you will give to the input, it will produce at the output. Okay, only one input is there, that will act as a mod 1 only. Yeah, okay. Okay, so this question is, what logic block should be placed at a point of X here so that the circuit acts as a mod 7 counter? Okay, okay, so the circuit acts as a mod 7 counter. So here the three inputs are given, and that here whatever the circuit option are given, either 3 input OR gate or 3 input NOR gate or 3 input NAND gate or 3 input AND gate. Okay, so for mod 7 counter we need to go 0 0 0 to 1 1 1, right? It is a 4 bit, so from 0 0 to, in order to count. So after this, that output has given to clear, right? All the flip flops clear input, that means after that it will clear. So whatever circuit here we are using, that means after 0 1 1 1 it must be 0. So Q3 is remains last one. So we need to choose any of the gate that input is given 3 input, that will produce output 0. So at which point, when the both, that means the three of them 1, then after that that must be clear, right? So which gate in these four, which gate the output will produce 0 when the all output inputs are high? OR gate will produce 1, already you know that when the inputs are high it will produce high, and NOR gate that can produce, right, 1 1 1, that will complement, but it will not. But when the NAND gate, in the case of NAND gate, whatever input you will apply, when these three inputs or two inputs are high, it will produce the 0 output. So when Q0, Q1 and Q2 are connected here, so that means when it will act as 0 1 1 0, that will clear. So NAND gate is the best option or possibility to produce a 0, because the Q3 has not connected. Q3 is the another output. and the Q0, Q1, Q2 is connected to the any of the gate. So they are asking for which gate will be suitable here. So that will, after this it will clear. So that circuit will act as a mod 7 counter. Okay. So option C is the correct answer. You can go through the options in this type of question. You can go through these options from which is the best suitable. So already here it is given mod 7 counter, so that means we need to count from 0000 to 011. So now we need to check at which gate it will produce 0 output, so that every flip flop will be clear. After that it will again start from 000 and will count 0 to 111. Again it will clear, so it will act as a mod 7 counter. Okay. So moving to the next question. In which mode can we provide data to all the flip-flops simultaneously? Parallel output mode, option 2 is serial input mode, option 3 loop back mode, or option 4 is parallel input mode. So in which mode can we provide data to all flip-flops simultaneously? So already we know that a flip-flop can store one bit data, right? So let's, for example, we can take 2 or 3 flip-flop, right? And here, in which mode can we provide data to all flip-flops? We need to provide data to all flip-flops. Okay, this one is a clock that can be connected, and you can take here it as a D flip-flop. Okay, mostly because it will act as a shift register order. So already we know that the flip-flop store one with data. A group of flip-flop is known as a register, right? Register. So already there are 4 types of registers. Or if you know that serial input, serial output, that means input is given serially and output will be taken here from serial, that is connected like this. And another one is a serial input, parallel output. Serial input parallel, that means input is given to serially like this and output will be taken at every flip flop. And another one is a parallel input, serial output, right? That means parallelly every flip flop we are giving the individual data and we are taking the output serially. And another one, last one, parallel input, parallel output. That means individually we are giving the input and taking the output at each flip flop. So they are asking in which mode can we provide data to all flip flops simultaneously. That means individually at which mode we are providing the data. So that would be only the parallel input mode, because they are not asking for taking out the data. They are asking only for providing data. So we will provide the parallel input mode to all flip flops simultaneously, right? So parallel input mode, that's why option 4 is the correct answer. Okay, so moving to the next question. I hope you understand. So here also it is given the 4 types of the shift registers. So which of the following is a function of shift register? So option 1 is to convert digital information into analog. Option 2 is to store bits and bytes of a binary data temporarily. Option 3 is to convert serial digital information into a parallel or parallel digital information into serial. Option 4 is to control voltage level according to the clock pulses. So what is a function of shift register? So already in the previous slide I have told you there are 4 types of shift register, that is serial input, serial output, serial input parallel output, or parallel input serial output, or parallel in parallel output. So that means the serial to parallel conversion or parallel to serial data conversion. So a shift register can be used for parallel to serial conversion or serial to parallel conversion. it also used for delay, right? So only option 3 is the correct answer to convert serial digital information into a parallel or parallel digital information into a serial based on which type of shift register we will use. Okay. Okay, so moving to the next question. So next question is a 4-bit shift register is shifting data to the right, okay, to the right for every clock signal. The serial input D is derived using XOR gates. The input is derived using these XOR gates as shown in the figure. Okay, so considering the initial count of the register is 0001, that means Q0, Q1, Q2 and Q3, right? It is 0001. After how many clock pulses it will be back to the initial position. That means initially it is in this position, but after how many clock pulse it will again come to the, let's see, it is a clock. Okay, now, okay, so initially it is in this position 00. So how many after how many clock pulse it will again come to 0001. So let's check from here. So first we need to XOR Q2 and Q3 and then output of this Q2 given to the next XOR, and then that output and Q0 XOR and that output is connected to D. That means first flip-flop. Okay. So now when the first clock pulse we are applying, then we need to XOR Q2 and Q1. That means 0 and 1. Okay, because initially it is stored. So if you XOR 0 and 1, the output will be 1 only, right? Because here it is a XOR gate. So 1. 1 again. 1 we need to XOR with Q0. So Q0 is 0. So 0 and 1. Again 1. The output is here 1. Here for first clock pulse I am taking here, it is 0, it is 1, right? So output will be 1 and here it is 0. So 0, 1, 1 will be there and that will go on to first, right? And the output is the input first flip flop, then it is a D flip flop. So whatever we are giving 0, output will be 0. If we are giving 1, the output will be 1, right? So that means output of this Q0 will be 1. So 1, 0, 0. Now shift these bits 0, right? Now if we move, it is correct, right? Now if we are giving to the next clock pulse, then again we need to XOR Q2 and Q1. So 0, 0 will be 0 and now 0, 1, 1. It is given to the next input of the first flip flop. So and shift next 1, 1, 0, 0, right? To the next clock pulse again XOR Q2 and Q3 and then output of this XOR with Q0, right? So 0, 0, 0 and 0, 1, 1. So 1, 1, 1, 0. Now again to the next clock pulse XOR Q2 and Q3 0, 1, 1 and 1 XOR with 1. So again 0, 0, 1, 1, 1. Now for next clock pulse again 1, 1 XOR Q2 and Q3 1, 1, 0 again 0 XOR with Q0, that is 0. So 0, 0, 0 0, 1, sorry 0, 0, 1, 1. Now again XOR Q2 and Q3, that is 1, 1, 1, 1, 0. And if we XOR with again Q0, so again it will 0. What is 0? So 0, 0, 0, 1. Okay, so initial is 0, 0, 0, 1. Again, after 6 clock pulse, it will again back into the initial position. So, how many clock pulses are required? Total 6 clock pulses are required to get back into the initial position. Okay, so option 2 is the correct answer for this question. So I hope all of you understand this question. Can we move to the next question? Are you getting? Okay, so I hope all of you are getting. So moving to the next question. So next question is, a 3-bit shift register is shown below. Here it is given. To have a content 000, again the number of clock pulses are required. What number of clock pulses are required to again back to the 000 position? So here clock pulse are given, reset is given, and it is a D type flip flop, and again it is connected to the complemented output, the last flip flop to the first flip flop input. Okay, so already Q1, Q2, Q3 it in position 000. So when the clock pulse we are applying, it is a clock pulse 1, then it is in position 000. When the clock pulse is applied, here it is 0, so it will be complemented 1, right? Already we have solved one problem like this, I think, in the previous. So 1, and that 1 will be given to the input to the first flip flop. So output of Q1 we can take as a 1. So 1, and now shift to the next. Again the next flip flop, it is 0. So again it will convert to 1. So 1, 1, 0, right? Now again it will invert. So 1, 1, 1. Now here the output came to 1. So it will complemented as a 0, right? In the next clock pulse. So 0, 1, 1, right? Now the next clock pulse, again it will complement and shift 0, 0, 1. And now again if we apply next clock pulse, so it will again complement. So 0 complement and shift. So 0, 0, 0. So it will again, if we apply it, so again it will act like this only if we further apply. So in the 3-bit shift register, to have content 000 again, how many clock pulses are required? That is 6 clock pulses are required to again in the back to the 000. Okay. So I hope all of you are getting. Okay, you are asking about how to decide MSB and LSB. Okay, so you can take any of, but if you check this, because here they are asking only for clock pulses, so in that case there is a no problem, but you can take either this side or this side. Most of the cases it is given, but here it is not given, so you can take from any of side. Okay, you can take MSB this side. Most of the cases MSB this side and LSB this side. Okay. So here it is not given, so you can take it. Okay, so moving to the next question. Next question is, how many JK flip-flops are required to achieve a frequency division of 8? So how many JK flip-flops are required for frequency division of 8? So already we know that the number of states for mod n counter is n is equal to 2 to the power n, right? Here it is given 8, where n is the number of flip-flops, right? So here it is given state 8, because flip-flops, if we count, if we add some input, that will act as a counter, right? So in order to find out the number of flip-flops, so here frequency division of 8 is given, so that means mod 8 is there. So 2 to the power, if we convert 2 to the power 3, right, is equal to 8. So n is equal to 3 flip-flops are required for frequency division by 8. Yeah. So option 3 is the correct answer for this question. Okay, so moving to the next question. So next question is an 8-bit binary ripple up counter with modulus of 256 is holding. The count, this count is hold. What will be the count after 135 clock pulses? Okay, so here it is given an 8-bit binary ripple up counter with modulus 256, right? That means it will count till 0 to 257, right? Now currently it is holding this count 0, 1, 1, 1, 1, 1, 1, 1. So what is the decimal value of this? Can anyone of you convert this? What will be the decimal value of this binary? Is 127. That means currently it is hold the decimal value 127, right? It will be the 127 if you count, and it is 8-bit binary up counter with modulus 256. That means that will count till 250, 0 to 257. Okay, so currently it is holding this value, right? So after 135 clock pulse, what will be the value? So currently it is 127, and if we add after 135 in this, then we will get what will hold at after 135 clock pulse. Okay, so what will be the value? 266, 262, right? If we add, currently it is holding 127, but they are asking what will be the count after 135, right? After this, it will the count after 135 clock pulse. So the value will be 256, 262, right? But here we are able to count only 0 to 257, right? So that means, so number of clock pulses required to count 262, 262. So after 257, after 257, it will again start counting from 0000 to again it 257, right? So at 257 clock pulse, it will be the 000000001. 8-bit will be, because 8-bit binary ripple up counter. And at 258 clock pulse, it will change to the next stage 000000010. And at 259 clock pulse, it will count 000000011, right? At 260 clock pulse, it will count 100. Okay, and at 261 clock pulse, it will count 101, and at 262 clock pulse, it will count 110. Okay, yeah, 0, that means 6, yeah. Okay, so it will count at 266 pulse is this value. Okay, because after 257 it will start again at from beginning. Okay, so here it is given it is stored currently, but we have to check after this 135. So that's why I have added 127 to, that means 127 clock pulses are completed. Now after 135 clock pulses, what will be the value? So value, if we count, that is 262, but here it is given modulus 256. So after 256, sorry, 255, 256, it will again start counting, right, from beginning 0000 to again 257. So here after 257 again, that's why we have taken like this. So at 262 pulse, clock pulse, we will get this value. So check it from the options. So option 3 is the correct answer. I hope you understand this question to how to solve. Yeah, 255. Yeah, I mistakenly written 2. I thought that it is 258. Yeah, it is 255. Yeah, correct. It is will be the 255. 0 to 255. It will count. Okay. So moving to the next question. So next question, shifting a register content to the left by 1 bit is equivalent to division by 2 or addition by 2. Option 3 is multiplication by 2 or subtraction by 2. What will be the answer? Please answer in the chat box. This is a simple one. Yeah, option 3 the correct answer. But how? We will take one example and we will show that. Okay, shifting a register content to the left by 1 bit is equal to multiplication by 2. But how? Let's take one example. Okay, let's decimal value 36. Okay, what is the binary equivalent of 36? This is the original bit. So it is 0 0 1 0 0 1 0 0. If you change this binary to decimal, you will get 36. If we shift one bit left, shift one bit left. This is a original bit. If we shift, that means shifting this side, right? Shift one bit left, then we will get 0 1 0 0 1 0 0 0, right? Now again convert it into a decimal, then you will find out what will be the original bit 36. If we take decimal equivalent, you will get 2 2 2 3 1 2 3 4 5 6 64 plus 8, right? We will get 72. That means original value is 36, but if we shift to one bit left, you will get 72. Means 36 into 2 is equal, that means multiplication by 2. If we shift one bit left, we will get a multiplication by 2 bit. Okay. Okay, not clear. Okay. So let's take any value. Okay. I have taken the decimal one. So you can take any binary, because in the shift register we are going to give 0 in the form 0110, right? If you have seen. So just take any number and find its equivalent decimal number, because of we need to check whether if we are multiplication or a division by 2. So I have taken this binary bits. Okay, now check shift with one bit left, because here it is given shifting a register content to left by one bit. That means shifting this side, right? I have shifted this one bit. Okay, so let's again shift it this side. So it will go on to this side. So it will 0, 1, 0, 0, 1, 0, 0, 0. You will get this one. After shifting one bit left, what will be the value you will get? Shift this one, you will get this one. Now convert it into a decimal form in order to check whether it is a multiplication by 2 or division by 2, and also find the equivalent decimal of this bit. Then it is an example in order to make you understand, while shifting the register content to left by one bit, what will be the, how it will act, whether it will act as a multiplication by 2 or division by 2. So is it clear or not? Okay. Okay, now clear. Just take one example, take any bit, okay, and shift one bit to the left. Then check how you will check, by converting the binary to decimal. Then you will get the whether it is a multiplication by 2 or division by 2. Similarly, if you shift this bit to the right, then check what will be the value you will get, whether it is a division, multiplication, addition or subtraction. You can check it. That one also. Okay. Okay, so moving to the next question. So the minimum number of flip-flops required to construct a counter to count up to 200 decimal. Okay, so minimum number, we need to find out the number of flip-flops that count up to 200. Okay, so already we know that that will act as a mod 200 counter. Yeah, so here it is, you can say that mod 200 counters, and is the number of states, right? Must be 2 to the power n, right? That must be greater than equal to 2 to the power n. So here it is given 200. So it must be, n is the number of flip-flops. So what will be the value? If we, that must be equal to 200, it must be 2 to the power 8, right? That means 2 to the power 8 means 256. If we take 2 to the power 7, what will be the value? What will be the value for 2 to the power 8? Sorry, 2 to the power 7? 128. So 128 is much less than the 200. Okay, so that's why we will take 2 to the power 8. So that can be able to count every stage. So 8, n is equal to 8. That means 8 number of flip-flops are required to construct a counter to count up to 200. Okay, so option 3 is the correct answer for this question. Okay, so I hope you understand it. So moving to the next question. So next question is, a mod 2 and a mod 5 up counter when cascaded together results in a mod counter. What will be the result? So whenever two counters having mod A, okay, I'm writing whenever two counters having mod A and mod B cascaded together then resulting counter will be mod A into B. The overall counter will be act as a mod A into B. So mod, here mod 2 and 5 is given. So mod 2 into 5, that means it will act as a mod 10 counter. Okay. So here mod 10 counter. Okay, somebody is asking some question. Yeah, yeah, it is mod 10, right? Can we connect counters in a parallel for any case? Yeah, you, no. If you connect, that will not only, that will count only that number only, individual. You will take the, yeah, yes, someone is want to ask. Yeah, you can ask in the chat box or you can unmute yourself and ask. Okay. Yeah, you can connect in any case, but you have to take the maximum one. Okay. That is, if you connect in mod 2 and mod 5 in a parallel, so the resulting counted only the mod 5, not 2. Because if you are taking the mod 2 only, so the other numbers you can't count. So you have to take the maximum one. Okay. People are connecting. Yeah. Okay. So moving to the next question. So next question is also based on the number of how many flip-flops are required to design a mod 258 counter. Okay. So already you know that how to solve this type of question because we have solved many this type of questions. So please answer in the chat box for this question. Yeah, it is a 9, not 8, I think. Because here it is given mod 258 counter we need to design. Okay. So that means that will count to 0 to 257, right? So n must be less than 2 to the power n, right? So what will be the value? Here 258 is given. So state is 258. That must be greater than, here n is the number of flip-flops. So what will be the value of n? So that can able to count till 258. 2 to the power 8 is 256. In that case, it will not able to count the two places. So we must we take 2 to the power 9 so that it can able to count all the states. Okay. So n must be equal to 9 in order to count the all states. Okay. If we take 8, then it will able to count only 256, 0 to 255. But here the mod 258 counter is there. So we need to take n is equal to 9. So 9 number of D flip-flops are required to design mod 258. Okay, so option 1 is the correct, not here. Oh, yeah, in the option it is given 2. Okay, sorry, but here it will be the 1. Okay, okay, so option 1 is the correct answer. Yeah, it is wrong here. I forgot, I can change. Option 1 is the correct for this question. Okay. Okay, so this is the last question for this week. So if you have any doubt, you can ask. Otherwise, we can close the session. Yeah, if you have any doubt, okay, okay, so that we can close the session. So thank you everyone. Thank you for joining this session. Please share some more practice problem from for exam. Okay, I will share. Okay, yeah, here I have taken 25 questions. Other three more TAs are also taking the classes. If you want to practice more and more, you can join their session also. And if you want some more questions, okay, I will post it in the that Google Drive. Other questions you can take from there also. Okay. 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 Yeah. Thank you, everyone. Thank you for joining. Yeah.
Thank you, ma'am.
Thank you.
No. No.
Okay, now you can leave the session. If you don't have any doubt, if you have any doubt, you can ask now. Okay. Okay. So yeah. Thank you, everyone, for joining this session.